Sorry, you go first, Colin.
I actually, for the homework, I
Hmm.
was having some trouble both with the question about throwing the football or ball based on just like you had the velocity and the height above it and the
Uh-huh.
angle, but that was about it, as well as the problems involving trying to get across the river with the across like bodies of water with like uh
A
the
running
velocity of
current.
the water going up a different direction. Will we
Right.
be covering that tonight? Because I don't remember us covering that specifically, and when I looked it up in the book, it was just confusing.
Yeah, so we sort of covered it in chapter two when I did the relative velocities, basically. Remember, the VAC is equal to VAB plus VBC, with the
Yeah.
extra added that VAB is equal to negative VBA. That's sort of it. That being said, it's pretty. It's still not trivial to apply that to the problem with the lake, but yeah, we can certainly do that. I'm going to go ahead and try to pull up that homework set now, just to see if there's anything I can offer you assistance wise regarding that.
The main ones I was having issues with were I wrote them down.
Was it part one or part two homework?
Part two, I part one's fully done.
Okay.
Um, I was having some issues with
Crossing a river was one
yeah,
of them.
crossing a river number 3.35 and 3.83.
3.35 and 3.83. Gotcha.
I was also confused why it says the 3.83 is not considered for credit when it has is actually graded, but a lot of the ones that are say practice are in the graded section, so I'm not sure
Gotcha.
there's
I
a
don't
difference.
remember any of those be. Oh, okay, I see. Yeah, so the last one, two, three, four, five were supposed to be extra credit.
Oh,
And
okay.
so that included the projectile motion, PHET, the crossing a river, and delivering a package. But the other two that you mentioned, 335 and 383, were not. I think I'm looking to figure out, let me put it on the student view. Look at this problem and see if this is the one. Oh, the speed of a boat in still water. Yeah, that's not the same one that you were having problems with, I don't think. Or was it? Oh, yeah, that's
Uh,
3.83.
yeah, 3.83 and 3.35 were the two that I was struggling with.
Gotcha. Let's look at 3.83 right now. It says the speed of a boat in still water.
Uh-huh.
Darn it, I keep people are signing in, and I hit let them in, and it makes me lose my window. That's got this problem. It says the speed of a boat in still water is v. The boat is to make a round trip in a river whose current travels at speed u. So,
Yeah, essentially anytime you got brought up, that's where my I started getting confused.
gotcha. No problem. Let's see what I can do now. I'm gonna go ahead and change this wording of this problem. Sorry, I got to get my notes stuff ready so I can write down this. Today is the 22nd. God darn it. Okay, let's let more people in. Now I got to make this available. Hold on a second. Sorry about taking so long. Okay, so I'm looking at problem 3.83. I'm going to go ahead and share my screen with you guys. Let's do advanced iPad share. Now I'm going to do Screen mirroring. So this should pop up in a second now. 3.83. Whoa. Sorry about that. So it says the speed of a boat in still water is v. So velocity boat relative to the water is equal to v. The boat is to make a round trip in a river whose current travels at speed u. So the velocity of the river with respect to the earth is u. And the rule that I taught you about was the velocity of A as seen by C is equal to the velocity of A, leave a space, plus the velocity, leave a space, C. So notice how the outside subscripts match the two subscripts on the left, and now you want to notice that the middle two have to match each other. So that's the sort of rule here. And what they're asking for in this first problem is derive a formula for the time needed to make a round trip a total distance d if the boat makes the round trip by moving upstream and back downstream. So what we're going to do is I'm going to imagine that this is the stream, and I'm going to imagine that this is the velocity of the river with respect to the earth, which equals u. Okay, and now I'm going to say I'm going to start here, and then this distance from here to here is d, and this is the turnaround. So my trip is going to be from here to here. Oops. From here to here.
Wait, it's not a, I thought it was asking if it was like the other side of the river, not the same.
Initially, they're talking about moving upstream and downstream. I think the second part is when you go perpendicular to the stream, if
Okay.
I remember correctly. And
Right.
yeah, this is what it says. Derive a formula for the time needed to make a round trip a total distance d if the boat makes the round trip by moving upstream and back downstream. So what they want to know here is t equals question mark. So that's what I'm going to shoot for. Now, what I have to realize is the velocity of the boat with respect to the earth has got to equal the velocity of the boat with respect to the water plus the velocity of the water with respect to the earth. Now, what we have, oh, excuse me, it should be river, not water. I'm trying to use the same prefixes or, excuse me, subscripts as I did before. So this should be not that one. This should be the velocity of the boat with respect to the river, which we called water before, so I can just change that now. And the velocity of the river with respect to Earth. So to do that, I'm going to change this to be R. That's just a difference of me calling it water in one case and a river in another, so that doesn't really matter too much. So the key thing that you see here is that the velocity of the boat with respect to Earth, and Earth is what the distance d is measured with respect to, so that's why you have to have that one, is therefore equal to we do have the velocity of the river with respect to Earth is u, so this is going to be v plus u. And then on the way back, it's going to be the same thing. So this is, let's say left, or excuse me, going right. And now going left, what we can see is the velocity of the boat with respect to Earth is equal to the velocity of the boat with respect to the river plus the velocity of the river with respect to the Earth. But in this case, the velocity of the river is positive, but in the velocity of the boat with respect to the river is actually going to be negative v. So this one's going to be negative v plus u. Do you see that it's got to be negative because he's going back for the other trip?
Yes.
Okay.
The back the parallel one makes sense to me. It's the perpendicular one I was
Okay, gotcha. So well, I'll just finish this out real quick. So t right, which equals velocity equals distance divided by time. So time equals distance divided by velocity. That'd be d divided by v plus u. And then t left would equal d divided by u minus v, like that. So t total is equal to d over v plus d over u minus v, which you can go ahead and make this d over uh, u squared minus v squared. And in order to do that, I'd have to multiply by u minus v, so that'd be u minus v here. And then the other one would be d times u plus v, and this would also be u squared minus v squared. So you can now see it'll be du minus dv plus du plus dv in the numerator. Those are going to cancel out, and it'd be u squared minus v squared. So the result should be 2d over u squared minus v squared. So that should be the result that you get for the part A. Now, part B, we're 6 minutes in, everybody. If you haven't already done so, please, by all means, chat your first and last name so I have that for roll. And we are working on problem 3.83 from chapter 3, homework part 2, per a student's question. So that's what I'm working on now. Part B, it says derive a formula for the time needed to make a round trip of total distance. Ooh, sorry about that. The 2D, I was working it as if the total distance was 2D, not D. So I apologize for that. This should have been 1/2 D and 1/2 D. And then that would have fixed that. But that's obviously going to make other stuff questionable. So I'll just put that there. But you see the trick of what I was doing, so you should still be able to make that out. Now, part B, it says derive a formula for the time needed to make a round trip of total distance D if the boat makes the trip by moving directly across the river and back. So again, we're going to have the river like this, and we're going to say the river has a velocity of the river with respect to the earth equal to u. Now, what we're trying to do here is we're going to make this distance be d over 2, and the trip will first be from here to here, and then the trip back will be from here to here, though laying in exactly the same spot because they said derive a formula for the time needed to make a round trip, a total distance of d, if the boat makes the trip by moving directly across the river and back. So I would like to write this arrow exactly on top of the other arrow because that's what it has to be technically. But in order to do that, what we've got to do is we've got to aim the boat perpendicular to the path, or not perpendicular, but to an angle to make sure it goes directly across. So the velocity with respect to the water is going to have to be just plain v. Velocity of the boat with respect to the river is just plain v. But what we need based on that is we need the total velocity to be v, but we need this component of the velocity. Actually, we need that backwards. Sorry about that. When I pull it, when I go straight across on the way up, I am going to have to, yes, I'm going to have to sort of cancel out the direction that the river's going. So in order to do that, okay, I see what's going on. So in order to do that, what I'm really doing is I'm going to point my boat up and to the left like you see here, and that's going to have a component u this way because that's what's got to happen. I've got to cancel out the velocity that goes to the right so that I can land directly across the river. So I'm going to have to basically go at some angle theta. And then on the way back, I'm going to need to do the same thing. In this case, I'm going to have to again have a velocity component u this way that will cancel out the river's velocity. And again, this one's going to have to be v as well. So you can see that the actual velocity perpendicular to the stream, I'll say that's for part A, and velocity perpendicular to the stream, and I shouldn't say A, but I'll just say let's call it U. That's what I'll do. U for on my drawing it means up. So I'm going to say perpendicular but up. So V perpendicular up and then V perpendicular down. We can see that V squared is equal to U squared plus V perp U squared. So V perp U is equal to the square root of V squared minus U squared. And V squared is equal to U squared plus V perp down squared implies V perp down is equal to the square root of V squared minus U squared again. So that's the actual velocity that we're going to be traveling uh, along the distance d. So that's the one that matters. Uh, t for up is going to be d over 2 divided by v perpendicular up. So that's going to be d over 2 times the square root of v squared minus u squared. And t down is going to be d over 2 divided by v perpendicular down, like that. And that's going to also be d over 2 square root v squared minus u squared, like that. Therefore, t total, which equals t up plus t down, is going to be, we obviously have a common denominator, so it's going to be 2, just plain 2d over the square root v squared minus u squared, like that, divided by 2. So t in this case is just going to be d over the square root v squared minus u squared. Does that make any sense to you? And was this Colin?
Yes, it does. I think I got it. I The only thing I was kind of confused by was why the down triangle was kind of pointed that way and not flipped.
Oh yeah, that was just me drawing it backwards. I'm sorry. Yeah, you're exactly right. That should have technically been drawn this way.
But now that I see it's just a squared b squared c squared, yeah,
Yeah.
that makes more sense now.
Yeah, this
Uh,
would be V perpendicular down. Sorry about that. You're exactly right on that, by the way. I don't know why I drew it backwards. My brain wasn't processing
um,
pretty too well at that point. Anybody else have
uh,
any questions?
Yeah, I had a question about our proctor test coming up.
Okay, yeah, go for it, Daniel.
I have a, set time to be at a testing center 2 Saturdays from now.
Okay.
The Saturday before it's due. Would I have to contact you about getting the actual test, or do they provide that at the testing center?
You using a TCC testing center?
Yes, the one in Virginia Beach.
Gotcha. So when that time for that test comes available to me, I submit a document that's got all your guys' names in it, and then automatically all of you will have access to it through that through all the testing centers, not just the one that I send it to. I send it to testing center, and it goes to all of the facilities. And they'll have passwords so they can enter the password so that you can access the test because you can't. I mean, it'll be up there and you can see it, but when you click on it, it won't let you in unless you know a password. So the testing center knows a private password that they put in for you, and then you'll take it. So yeah, and not only that, when you register for it, they normally send me an email saying that you've got it, but they normally do it within a couple days beforehand. So I haven't gotten that email yet, but that's probably because you're 2 weeks out.
Okay, sounds good. Thank you.
All right, and feel free to remind me if you don't hear anything soon from me or whatever, or if you don't hear anything by let's say the Thursday or Wednesday before you're going to take it, you might want to refresh your discussion with me just to remind me about it.
All right, sounds good. Thank you. Appreciate the help.
You're welcome. Colin, we can do some more questions afterwards, but is that good for right now? And once I finish with material, I can answer some more questions from the homework.
Yes, I was just wondering about when we can actually sign up for the proctor test.
For the face-to-face test, I think they allow
Yeah.
you, 3, 4 weeks in advance if you wanted to.
Okay.
The due date,
And
if I remember correctly, is like October 8th or something. So, and you'll normally have it a whole week before that. So, any of those days in there that fit in your schedule and fit in the schedule that you can get at a testing center, that should be fine.
we have to sign up. We just can't show up.
Yeah, they want you to make an appointment, mainly because they have certain rules that they want to explain to you, and they have certain hours. Like one of the rules is if I give you a test and I say you're allowed 2 hours, then they won't let you start unless you start 2.5 hours before they close. So little
Okay.
stuff like that, you have to bring a photo ID, and then also, like I said, you have to actually make an appointment. That makes sense?
I can send it in chat too, Colin, if you want. I just did it today.
Oh, cool. Yeah, thank you.
Uh,
Yeah, if you help him with that,
yeah,
that'd be awesome.
thank you.
Uh, Daniel, were you the other person that had a question when Colin first came on and you told him to go first?
Yeah, I just asked you
Okay.
that. It was the testing.
That's cool. I just want to make sure I got everybody. All right, so feel free to ask me the other questions again. I sort of remember them, and I'll probably remember them by the end of class, Colin, but we can work on some more after that. This top part for part A was actually done properly, but what I'd have to have just to make it look correctly is I'd have to have a 1/2 there, a 1/2 there, and then that would be a 1/2 and a 1/2 and a 1/2 and a 1/2. So you can see a lot of stuff is going to be a little bit different, but I think ultimately it should still be the same answer, except instead of 2D, it's just going to be D over U squared minus V squared. So anyways, hopefully that helps you enough on understanding that. What I wanted to do, does anybody have any other questions before I get started on the material? All right, so what I wanted to do was work another projectile motion problem, just a one that's kind of tricky for students, and I normally work it in symbols so you can see it really nicely. But I know that my students, majority speaking, my students, even in our calculus-based physics, do not tend to solve physical problems with the symbols as much as they do with numbers. So I'm going to try to establish this problem by actually solving it with numbers. So you'll see how to do it, but you can feel free to try to do it in a symbolic form if you want. What we have is we're going to imagine a tree. So here's a tree, and in this tree, say, is a monkey hanging. Okay, and this is a monkey hanging from the tree, just having a good time, not like nobody's being mean to him or anything terrible like that, right? But he's just hanging there, and we, being good parishioners and good animal lovers, we are wishing to actually shoot him with a tranquilizer gun so that we can inoculate him from some kind of disease or something like that. So what we know is going to happen is because the report of the weapon is, sort of loud, and because the bullet doesn't go, or the tranquilizer dart doesn't go anywhere near as fast as the speed of sound, what's going to happen is essentially instantly when I fire the rifle, the monkey's just going to instinctively let go of the limb and fall. I'm going to say the monkey we can treat it like a point object, by the way, and I'm going to say the monkey has a height h equals 4.00 meters. And then I'm going to imagine that my bullet is firing at some angle theta, and hopefully it's going to hit it. Okay. Now I'm also going to add that this distance right here is 8.00 meters. Okay. And make sure I have enough time to do this. 4 times 4.9, 16 times 4.9. Yeah, that should be fine. So actually, I'm going to try to make sure. I was planning on doing this with numbers, but I hadn't worked out the numbers, so I just want to make sure everything works out all right with this. 4 times 2 divided by 9.8. That gives me a distance of 0.816 square root. Let's say the velocity of the let's say the velocity of the tranquilizer gun is 60 meters per second, something like that. That's pretty fast, plenty fast, anyways. So the big question is, knowing that the monkey is going to drop from the limb as soon as I pull the trigger, and I say instantly because we're going to ignore the finite difference between the speed of sound and stuff. So if that's the case, should we aim the rifle above the monkey or below the monkey or directly at the monkey? That's the big question. Where should I aim the rifle? That's the big question. So I'm going to show you how I go about doing this. We'll start off with solution, and what we need is the position of the dart has got to equal the position of the monkey. Okay, so that means x of the dart, comma y of the dart has got to equal x of the monkey, y of the monkey. Okay. Now we can actually represent equations, or write equations to represent these dimensions xd, yd, xm, and ym. And to do that, I'm going to imagine a coordinate system right here in which this is the x-axis and this is the y-axis. Ignore the fact that some of these arrows don't seem to hit the origin. We're taking off straight from the origin here. So that's actually what we're imagining as far as our angle theta goes. It's firing from there. And with that in mind, we can say that the x of the dart, remember the key to solving projectile motion problems is that the only acceleration that you have happens in the y direction, and that acceleration is g, and it points downward. That means the horizontal position is just given by the velocity that it has horizontally, which is the horizontal component of projectile velocity, times the time plus the initial x zero. So x for the dart should be equal to x dart 0 plus v 0x times t. Now we can see from my diagram that this initial position of the dart really is 0. And we can also see that V0x is equal to 60.0 meters per second. In other words, I'm pretending like that 60 is 2 sig figs. Meters per second times the cosine of theta, and theta is what we're solving for. And V0y is equal to 60.0 meters per second times the sine of theta. So with that in mind, I get 60, and I'll just leave the units off right now, but I get 60 cosine theta times t. That's the x position of the dart at all times. Okay. So at t equals 0, that's really when we're going to fire it. So it'll be meaningless until t equals 0. But from t equals 0 on until it hits the monkey or misses the monkey, this equation is going to be valid. Similarly, the x equation for the monkey's is just going to drop straight down, so he shouldn't have any horizontal component of velocity whatsoever. So x of the monkey is just going to be 8.00 meters, and that's it. Now we can go ahead and set xd equal to xm. And when we do that, we get 8.00 meters is equal to 60.0 meters per second times cosine theta times t. So in principle, we can see that t would actually be equal to 8.00 meters divided by 60.0 meters per second times cosine theta in the denominator. So I'm going to call this equation 1. It's going to come in handy because I'm going to have a time dependence in my y. So now I want to set up equations for y for the monkey as well as for y for the actual dart. So y for the dart is just equal to, I'm going to use the typical kinematic equation, 1 half a sub y t squared plus v0 y t plus y0. And by our diagram, we see y0 is already 0. And I can go ahead and say this is going to be negative 4.90 meters per second times t squared plus 60.0 meters per second. I'm going to write it a little differently than I did last time. I'm going to put the t between the velocity and the trig function, and then the 60 is going to be multiplied by the sine of theta. So that's the y position of the dart at any particular time. Now I need the y position of the monkey. Well, the monkey has an initial y position that's quite different. But it's still going to be 1 half a sub y t squared plus v0 y t plus y0. But in this case, y0 is going to be 4.00 meters. I know that 4.00 did not come out well. So it's going to be 4.00 meters. The initial y velocity is actually going to be 0, but the acceleration is still going to be negative 4.90 meters per second times t squared plus 4.00 meters. So now I can set y dart equal to y monkey at a particular time, and when I do that, I get negative 4.90 meters per second times t squared plus 60.0 meters per second times t times the sine of theta. That's all equal to negative 4.90 meters per second times t squared plus 4.00 meters. I think you can see that the 4.90 t squared appears on both sides. So those two cancel each other out. And we end up getting instead just 60.0 meters per second times time times the sine of theta is equal to 4.00 meters. I'm going to call this equation 2, and now I'm going to plug 1 into 2 because 1 is the time required given the velocity uh, that the tranquilizer dart has. T from equation 1 is the time required for the dart to actually reach the vertical line that the monkey falls along. So I can plug that time in, and when I do that, I get 60.0 meters per second times. Now, equation 1 was 8.00 meters over 60.0 meters per second times the cosine theta. And then I still have the sine theta that's there originally, and all of this has to equal 4.00 meters. Now what we can see is the 60 meters per second cancels out with the 60 meters per second, and I can divide both sides by 8.00 meters, and what I get is sine theta over cosine theta. Anybody want to tell me what sine theta over cosine theta is?
Tan?
Yep. So there's tangent theta is equal to 4.00 meters divided by 8.00 meters. And I think you can tell, given this triangle right here, that this angle right here, theta, is aiming directly at him because you can see its tangent theta equals opposite over adjacent, and the opposite is 4 and the adjacent is 8, and that happens to be exactly how high up he is, 4 meters, and exactly how far over he is, 8 meters. Therefore, you aim directly at the monkey. And the bigger point that I'm making with this problem is to let you realize that uh, the acceleration in the vertical motion is completely disconnected from any kind of motion horizontally. And even if you combine it with a vertical component of velocity, it still acts exactly the same way. So the fact that I fired this up at some angle theta means that neither the vertical component of velocity nor the horizontal component of velocity is going to be 60, but both of them be something, non-zero. And the fact that it's non-zero might make you think that, oh, it's firing upwards with a non-zero velocity, so gravity's going to act a little differently. No, 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 not at all. Gravity's going to act the exact same way on the tranquilizer dart as it does on the monkey, even though the tranquilizer dart was shot upward and to the right, whereas the monkey just drops. And that this shows that basically, hey, gravity acts the same whether you're moving up, moving down, moving left, moving right, moving diagonally up, moving diagonally down, or not moving at all. Gravity's always going to act on you the same in such a way that your velocity is going to increase in the downward direction by 9.80 or decrease in the upward direction by 9.80. Any questions on that one? All right. So there's just a last problem that I wanted to solve for you regarding projectile motion. Hopefully that'll help you a bit. We seem to possibly have another homework problem that we're going to work at the end of this. So if Colin still has a question at the end of class, we'll work that as well. But we are starting into chapter 4, and that's called dynamics, Newton's laws of motion. So as I told you, chapter 2 and chapter 3 were really just kinematics. We were talking about how does motion result in new velocities, new positions, and stuff like that by just understanding what the velocity initially is and what the acceleration is and how much time you're allowing to unfold. With those parameters, you can tell what the velocity will be and the acceleration will be at some time later. but that doesn't take into account anything that lets us learn, well, what actually causes velocity or what actually causes an acceleration. The study of what actually causes a acceleration is the dynamics portion. The kinematics is just the study of motion without respect to whatever caused it. So now we're going into dynamics, and it starts off with two really good opening chapter questions. And I want to remind you, you're always supposed to read these questions, think about them, come up with an answer, and then keep that answer in your mind until you read through the whole chapter, and then correct yourself or pat yourself on the back for getting the right answer. So here's the first one. A 150 kilogram football player collides head on with a 75 kilogram running back. During the collision, the heavier player exerts a force of magnitude F sub A on the smaller player. If the smaller player exerts a force F sub B back on the heavier player, which response is most accurate? A, FB is equal to FA. B, FB is less than FA. C, FB is greater than FA. Or D, FB is equal to zero. Or E, we need more information. So again, I don't want you to answer that out loud or even typing it in. I just want you to think about it. And then there's another question, a line by the poet T.S. Eliot from the book Murder in the Cathedral has the women of Canterbury say, the earth presses up against our feet. What force is this? And the choices are A, gravity, B, the normal force, C, a friction force, D, a centrifugal force, or E, no force. They are being poetic. So just want you to think about those as we continue talking about the chapter and as you read it. And then I want you to come up with your own answer. Hopefully, you already came up with it, but I definitely want you to come up with your own answer before you run into the right answer by reading. So do be thinking about that. Now we're going to move on to Newton's three laws of motion. I will read them as they're stated in the book. I will tell you them in my own words, and I want to give you the same warning I give my face to face classes. And that warning is if you open a textbook and you see a whole chapter dedicated to a law, or even a section of a chapter dedicated to an equation or a law or a principle, then the first thing that should happen in your head is some kind of bell should go off and say, hey, you need to memorize this. Okay. I want you to do that because I don't want you to make the mistakes I did. I basically thought I wasn't going to be able to memorize anything, so I never memorized anything. And mainly because my grandmother had been diagnosed with Alzheimer's, so I was pretty convinced that I was going to have Alzheimer's at a very young age, and I needed to figure out some way to deal with life without remembering stuff. So I decided I just wasn't going to memorize stuff anymore. Later, I realized that the memorization is going to happen no matter what, and it's actually very important. So the main thing is I took a lot of tests where teachers were trying to really be nice and give us, hey, here's this first question on your first test in graduate school, and it's supposed to be a chucker, but because I had this philosophy that memorization wasn't meaningful, I literally missed out on like a free 20 points on a test. So I don't want you guys making that mistake. So, just as a rule of thumb, if you ever see a chapter or a section of a chapter named after some principle, some equation, or some law, then you need to assume that you're going to have to memorize that because later on I might just ask a silly little question like state Newton's three laws of motion and label the first one as the first law, the second one as the second law, and the third one as the third law. Okay, that's very typical. And not only that, I would tell you, I'll go even further. Over the 2 semester sequence that you're having here, it would not be unacceptable or even out of the ordinary for me to ask you a question as follows. State Newton's three laws of motion, state Newton's law of gravity, state Kepler's three laws of planetary motion, state the zeroth law of thermodynamics, state the first law of thermodynamics, state the second law of thermodynamics, and state the third law of thermodynamics. Okay, so by the end of the semester, you should have all those in addition to Maxwell's four equations. So you could also add state Maxwell's four equations to it. All of those are things you should have memorized and be able to pull them up every day of the first semester and every day of the second semester. So please do that. We're starting off with force, and I want to tell you that a force was something that Aristotle had come up with in his laws of physics. Again, physics was not a word that was even popular in the time of Newton, much less in the time of Aristotle or Galileo. So they would have called it, natural philosophy or something along those lines. But the main thing is, in those times, they did have a force. In the case of Aristotle, he pictured that in order for an object to move, you had to have a force sustain that motion, unless the motion was a natural motion. And natural motion meant an object trying to get to its normal place. And if you remember, you've probably heard of, the elements used to be earth, wind, fire, and water, and Mila Jovovich, the fifth element, also called the quintessence, which was the heavens. But those first four involved something great. So you had earth, and yes, in the time of Aristotle, they very much knew that the earth was spherical. But the idea was things made of earth were trying to get to the center of the earth. So if you saw a tree limb, which is partially made of earth, and a person was holding it up, and then all of a sudden they let go of it, then the tree limb would fall towards the center of the earth, and that would be called natural motion because it's matter going to its natural place, and that didn't require a force. However, if you took a tree limb and you wanted to throw it down, then part of that help would actually come from natural motion. But part of it would also have to come from violent motion, and violent motion was the one that required a force to sustain it. So Aristotle would have taught that the tree limb would naturally fall at a rate proportional to its mass or to its weight. Whereas in the case where you threw it down, it would fall naturally at that rate. But when you threw it downward, you would actually allow it to go at a greater rate, and that would require a force. Or if you, for instance, wanted to drag the limb across the ground, it's not seeking out the center of the earth. So that again is violent motion. And as soon as you stop applying a force to it, the limb would come to a stop. So that was the way they saw that. And all that, of course, included the four elements and all that good stuff. But ultimately, they did have an idea of force. Now, what Galileo went and did was he studied motion. He was put in in-house arrest after basically getting in a little bit of trouble with the courts after predicting. He basically got in a little bit of trouble for he wrote a book that he asked for permission that he could write it. He asked a cardinal specifically. The cardinal gave him permission to write the book. Then he wrote the book, and in the intervening period, that cardinal actually became the Pope. So that was a good thing because that cardinal happened to be a personal friend of Galileo's, and probably the reason that he wasn't burned at the stake as opposed to put in house arrest. But the main thing is, he was threatened in that court case and told he wasn't able to teach about the motion of the planets anymore. So he decided that he'd spend the rest of his life trying to understand motion because when he had made his telescope that he read about, he did not invent the telescope, as a lot of teachers will teach you. Galileo did not invent the telescope, but he made a telescope that was markedly better, and he seems to be among the first people to actually use a telescope to look at the heavens. And when he looked at the heavens, one of the things he found was that Jupiter had little moons around it. And of course, he named them after the Medicis because he wanted to shake them down for some cash. So he did. And of course, we now call them the Galilean moons, but then they were called the Medicean moons. But what he saw was that Jupiter, and in all models of the universe, the Aristotelian, the Ptolemaic, as well as the Copernican and all that stuff, all of them have Jupiter moving. And one of the main reasons that they said the Earth wasn't moving around the sun or some other object was by the idea that if a bird was sitting on a tree limb and saw a worm on the ground and the bird jumped off the limb and began to fly down to get the worm, if that happened and the Earth was moving, then the Earth would just leave the bird behind. That was their understanding of motion. And because of that, if the Earth was actually orbiting the sun or any other body, then birds would be left behind like that all the time. In the case of Jupiter, after Galileo looked at it with his telescope, he immediately saw these four satellites over, several day period, and he could see that they were moving at different positions after a certain number of days, and therefore it was obvious that unlike the bird that we predicted would be left behind, these objects were not left behind. So clearly they didn't understand motion that well, or at least that's the way Galileo took it. So Galileo said, I'm going to try to study motion. And he first looked at, like, an object falling. And I don't know, but if you look at that, it's not obvious whether this, when I drop this pin, does it immediately take off at some speed that really is proportional to its weight so that if I, for instance, tape two identical ones together, they would fall at twice the rate? Or if I tape three together, they would fall at the rate of three times. That's not really easy to tell. So he decided, hey, the vertical acceleration is what I want to know, but if I allow something to go down an incline, I can use the relationship of the opposite side to the hypotenuse to give me the acceleration vertically from the hypotenuse acceleration. So he decided he's going to study inclined planes and very gradual ones. He even created his own clock. It was a water clock where he would take a big vat of water with a stopcock on it, and he would weigh a pan in which the water would fall in, and he'd know what weight it is. And then when he wanted to start timing something, he would open the stop cock that would allow water to start pouring in the pan, and then when it got to the end of the thing that he wanted to measure the time of, he turned the stopcock off and then weigh the container with the water in it, and the amount of water in it was directly proportional to the amount of time. So if you got, one experiment took a pan of water and the other experiment took twice as heavy a pan of water, then the second experiment took twice as long. That's the way he ended up doing it. And what he discovered was that when an object rolls up an incline, it tends to slow down. When an object rolls down an incline, it tended to speed up. Therefore, he argued that if an object was rolling perfectly horizontally, it would neither speed up nor slow down. He expected it would go forever. And then he tried experiments to verify that. So he would build a ramp that would allow an object to roll down it, and then it run into another ramp that would allow the object to go up a ramp. And what it looked like to him was that the object that he sent rolling down the hill was trying to go back up the hill and get to the exact same height that it left. But he could see that it was bumping and skidding and things were messing it up. So he'd polish the track really well and he'd smooth out the ball really well. And then he'd see that it get closer to that original height. And then he'd do it some more polishing, more sanding, and it get even closer still. So he reasoned that if there was some way to completely get rid of all the extra frictional forces acting on the ball, then it would be natural for the object that's going to roll down an incline to continue rolling up an incline until it got to its original height. Therefore, if the second incline was in fact not a incline at all, but perfectly horizontal, he expected it would go forever. So he came up with an idea that was called Galileo's law of inertia. And he said it's as if an object has an inertia, and that inertia is a reluctance for an object to change its state of motion. So an object will tend to go at a constant speed in a constant direction unless there's a net force added. Newton's first law says an object in motion tends to stay in that state of motion unless acted upon by a net external force. You can shorten that since we know the vector quantities. We can say an object will tend to maintain a constant velocity unless acted upon by a net external force. That is Newton's first law. Again, I would just memorize one of the versions in the book. But notice in doing this, we had to come up with an idea of force, and we had to use the word force. And I'll tell you that a definition of force is an object that can produce acceleration. So an object or an action that can produce acceleration is what we define a force to be. And they have a nice little picture of a young lady pushing a grocery basket packed full of watermelons. Don't really know why. And then we see a box of olive oil, a case of olive oil containers, in fact, being pulled across a tabletop with something like a fishing scale. Okay. And what they're showing there is yes, when you take and pull on a string that's tied to a case of olive oil, that's going to require some force to pull the olive oil. And in this case, it looks like it's going to be about 2.7, 2.8 newtons, because that's going to be the unit of force that we're going to talk about. So, with that in mind, let me give you some more information. First, Newton's first law, an object in motion tends to stay in that state of motion unless acted upon by a net external force. Then Newton's second law is the law that helps us when the force is not zero, because Newton's first law is basically what happens when the net force is zero. The net force is zero, then the velocity doesn't change. But you can make the contrapositive of that, and basically what you reach is the conclusion that if the force is not zero, then the object will accelerate. So we need Newton's second law, and Newton's second law I write like this: the summation of the forces, notice the vector symbol, is equal to mass times acceleration. Later, we'll learn that this is not a complete version of Newton's second law. And in fact, we should at least put the acceleration as the second derivative of the position vector with respect to time. But not only that, if the mass isn't constant, this equation is not even valid. So we'll learn in chapter 9 the more valid equation. But right now we're going to take that. Now, we can also solve this for A, and then it's more written more like the way Newton stated it. And basically, it's this: it basically says the acceleration an object will receive, an object of mass m will receive, is directly proportional to the net force acting on the object. So that's what that sigma F means. That means add up all the forces acting on it. That's why we're using the sigma symbol, which looks a lot like the summation symbol that we're used to from algebra. So the acceleration is directly proportional to the net force and inversely proportional to the mass. So this is the thumbs up, thumbs down scenario, because you see the acceleration is on the numerator on the left-hand side of the equals, but the mass is on the denominator on the right-hand side of the equals. That's the hallmark of thumbs up, thumbs down. The hallmark of thumbs up is numerator equals something in the numerator, or even denominator equals something in the denominator. In this case, we have A, which can be written as A over 1, so that you'll see A really is in the numerator. And then you see the net force, the summation F, that's also in the numerator. So acceleration and force, thumbs up, thumbs up. Does that make sense? Now he went further and said that the acceleration would act or would take place parallel to the net force. So once you add up the net forces acting on the body, you'll get a magnitude and direction. The acceleration is going to be exactly parallel to that direction. So it's an actual vector equation, even though there was no such thing as vectors when Newton wrote it. In fact, the vectors weren't discovered or created and imagined until the 1830s slash 1860 was when it was done. So that was done by, I think, Gibbs in America and Oliver Heaviside in Great Britain independently. All right, so now that we had that, I can tell you that the unit of force, so the unit of the left-hand side, summation of the forces, is just equal to the unit of any force, but that's going to be equal to the unit of mass times the unit of acceleration. So we know the unit of mass is the kilogram, and we know the unit of acceleration is the meter per second per second. So I'll go ahead and write a 1 in front of that, and then I'm going to say that's equal to 1 Newton. So that is the definition of a Newton. 1 Newton is 1 kilogram meter per second, or 1 kilogram meter per second squared. So that's the unit of force that we're going to use in the SI system. The unit of mass, as I told you already, is the kilogram. The unit of time is the second, and so on and so forth. There are other units, for instance, in the British system, which is what America uses, and dang it, I forgot the name of that other country. Oh well, it's in the South Pacific near Thailand. It's us and them. They're the only ones that use the British system anymore, not the Brits either. Okay. And in the British system, the unit of force is actually the pound, which we also use like this. And then the unit of mass in the British system is the slug. And you can probably see why nobody's heard of that because no one wants to be compared to slugs when they're when you ask them their weight. Uh, but that's basically what it is. Okay. Now, if we were in the CGS system, centimeter gram second system, then the unit of force would have been grams centimeters per second, and that is called one dyne. And you can see that 1 times 10 to the fifth dynes is equal to 1 Newton because in order to convert the gram to a kilogram, you got to divide by 1,000. And in order to convert the centimeter to a meter, you got to divide by 100. So you ultimately got to divide by 100,000, and that's what 10 to the fifth is. So 1 times 10 to the fifth dynes is actually equal to 1 Newton. So you can see the dyne is a really, really small sort of unit, if you will. Uh, the pound, by the way, 1 pound is approximately equal to 4.45 newtons. So that'll come in handy. I want to also tell you that weight, WEIGHT, the weight of an object is technically defined to be the gravitational attraction between the body and whatever planet or astronomical body it's sitting on. So if I'm on the moon, my weight is the gravitational affinity that the moon has for me. If I'm on the Earth, it's the gravitational affinity that the Earth has for me. If I'm on an asteroid, it's the gravitational affinity that the asteroid has for me. And you can see that that's going to change a lot. However, if I go to an asteroid or I go to the moon or I'm on Earth, in all of those places, my mass is going to consistently be, roughly 110 kilograms. I'm lying. I'm probably way more like 117 kilograms, but I'm giving myself a diet. So we're going to say about 110 kilograms. But that doesn't change from place to place to place. Okay. And in fact, how do we calculate it? Well, we can imagine a body in free fall. So here's free fall. We learned in chapter 2 about free fall, and free fall is what an object does when it falls with no other forces other than gravity. So what we have here is an object of mass m, and the only force acting on it is what we call, what's the W word that represents the gravitational attraction of something? The word that starts with W that represents the gravitational attraction to a body?
Wait,
Very good. This weight. So W equals weight, and that's all I'm going to call it right now because now I'm going to use Newton's second law. Summation forces is equal to mass times acceleration. We now know that's the only force acting on it, so that's going to be W. Can anybody tell me what the acceleration of a free object in free fall is?
9.8.
Yeah, it's the G that we use, right? 9.8 meters per second per second. So that's really what that is. So now, according to Newton's second law, we've got weight is equal to mg, and that's exactly right. That's the formula for weight. An object's weight is its mass in kilograms multiplied by 9.8 meters per second every second, in obviously in meters per second every second. Make sense? All right, so now we've talked about forces a little bit. We've talked about Newton's second law a little bit. We've talked about Newton's first law. Newton's third law, I like to write this way, and it is the force on object A as a result of object B. Notice how I've read that. The first subscript is the object that's experiencing the force. The second subscript is the object that's applying the force to the first object. that is equal to the negative of the force on object B as a result of object A. This is Newton's third law. This was Newton's second law. And Newton's first law, of course, was the sentence that I read to you, but we now know what these are. Another version of Newton's third law is for every action, there's equal but opposite reaction. Another way of thinking about it is this. If you actually try to kick a soccer ball and you kick a soccer ball with a force of, let's say, 300 newtons, then no matter what, no matter how awesome you are, that ball is going to hit back on your, upper foot slash lower leg with a force equal to 300 newtons, but the 300 newtons is going to act in the opposite direction. Okay. And a lot of people might say that this particular Newton's law is not worth that much, but I'll tell you, you can't solve even the simplest problems without Newton's third law. Even if I was, for instance, an android like Data from Star Trek, if I was an android like Data from Star Trek, not only would I have the full bevy of, hearing and seeing and smelling like Data does, which is like humans, but you could also imagine that Data could even have, a heads up monitor that he puts up for him to see internally that tells him when he pushes on something exactly what force he's pushing on it with, when he's running, how fast he's going, and all sorts of stuff like that. If you imagine me doing that and as Data, and I get up on the starting blocks of a race of a running track, even if I know exactly what force I'm applying to the starting blocks, I still can't calculate my acceleration. I know my mass. I know the force I'm applying to the starting blocks, but yet I still don't know how to calculate my acceleration. The reason why is the force I apply to the blocks is not a force on me. That's a force that I apply to something else. But if I use Newton's third law, then I can say, oh, well, the starting block is going to put a equal force on me in the opposite direction. So if I reach the conclusion that I applied a 500 Newton force to the starting blocks, then I can reach the conclusion that the starting blocks applied a 500 Newton force on me forward, and then I could put the 500 Newtons forward on the left-hand side of Newton's second law, put my 110 kilograms on the right-hand side, and then solve for A. So that's part of the importance of Newton's third law. Anybody have any questions on that? All right, now that we have that, there's a nice question in here. It's conceptual example 4.1. I'm going to discuss it with you verbally, and you can, of course, read it in the textbook, but it basically says Newton's first law. A school bus comes to a sudden stop, and all of the backpacks on the floor start to slide forward. What force causes them to do that? Anyone? I'll read it again while you are thinking, but feel free to either type in your answer or just blurt it out. You don't have to, get permission or anything. A school bus comes to a sudden stop and all of the backpacks on the floor start to slide forward. What force causes them to do that? Anybody?
No force.
It is no force. That's right. It's sort of a trick question. What's really happening is, in fact, a force that is in existence is not big enough to prevent them from moving. So, what happened was an object in motion tends to stay in that state of motion unless acted upon by a net external force. Well, the object was in motion. If the school bus was driving 35 miles per hour, then the book bags were going 35 miles per hour. Then all of a sudden the school bus, hits the brake or runs into something or something like that. If there's sufficient friction, then the book bags can stay right on the floor. But if the friction's not big enough, then the book bags are going to try to continue going 60 miles, or excuse me, 35 miles per hour as soon as the thing comes to stop. It won't succeed because there's still some friction. It's just not enough to keep it from completely stopping. So there really is no force that made them move. It's more like a lack of force, or as Galileo would explain it, which really doesn't explain it. He says it's as if the object has some inertia, some reluctance to change its motion. And that, again, is just some kind of word that you can put up there to make it feel better, make you feel better about, smacking Aristotle around or something. All right. Anybody have any questions on that? So we've talked about mass, we've talked about force, we've talked about the three laws of motion. What I want to now do is get work another problem to make you help you understand Newton's laws. So this is example 4.2, and it says estimate the net force needed to accelerate a 1,000 Newton, or excuse me, a 1,000 kilogram car. So F equals question mark for a one, M C is equal to 1,000 kilograms. I'm going to put a dot right there so we can pretend like it has 4 sig figs. Accelerated at 1/2 g, which is equal to 4.90 meters per second. So when you see a 1/2 g or a 0.25 g or a 1/4 g, they're meaning 1/4 of g gravitational acceleration, not g grams. And then in part B, they want to know the same thing for M apple is 200 point grams and A is equal to 4.90 meters per second. The solution is found by realizing Newton's second law, the summation of forces is equal to mass times acceleration. And part of the beauty of this vector equation is that that's a stand-in for three separate equations. The summation of forces in the x direction is equal to mass times acceleration in the x direction. The summation of forces in the y direction is equal to mass times acceleration in the y direction. And the summation of forces in the z direction is equal to mass times acceleration in the z direction. And now you're working with components of vectors instead of actual vectors. And these components can absolutely have negative values, whereas the magnitude of a vector does not have a negative value. But now let's go ahead and discuss this. So what we're imagining here is estimate the net force needed to accelerate a 1,000 kilogram car. So what we're thinking here is net force to accelerate it. So using Newton's second law for part A, we're going to say the summation forces in the x direction is equal to 1,000 point kilograms. So again, the decimal, just to remind you, there's 4 sig figs there. And then the acceleration is 4.90 meters per second every second. When you multiply those two, you end up getting 4.90 times 10 to the third newtons is the net force. So that's 4,900 newtons. For part B, the summation forces in the x direction is equal to 0.200 kilograms. Notice how I had to convert it to kilograms. Remember, all of our equations have to use the SI base units, which oddly enough has a prefix in the mass. Again, it's 4.90 meters per second every second because that's half a g. Now, this is the same thing as dividing by 10 and then multiplying by 2. So this turns out to be 1.96 newtons is equal to the summation of the force. So you can see, obviously, when the object weighed 1,000 kilograms, that's literally 5,000 times heavier than the 0.200 kilograms. So lo and behold, the force is about 5,000 times bigger. Namely, it's 4,900 versus 1.96. So that's completely consistent with F and A being or excuse me, F and or excuse me, A and M being thumbs up, thumbs down. So when the mass went up by a factor of 5,000, the force went, or excuse me, the acceleration either has to go down or the force could go up. Whichever way you have to look at it is fine. Anybody have any questions on that? I know I flubbed that last statement a little bit because I got confused and thinking we were solving for acceleration instead of force. But you can still look at it that way. The force and the acceleration are thumbs up, thumbs up. Uh, in this case, they both had the same acceleration, so that's not very helpful. But the force and the mass are also thumbs up, thumbs up. So the mass went up by a factor of 5,000. The acceleration, or excuse me, the force had to go up by a factor of 5,000. So that unflubs it, even though it was still ugly. Anybody have any questions on that? Okay, let's look at example 4.3. This one says, what average net force is required to bring a 1,500 kilogram car to rest from 100 kilometers per hour within a distance of 55 meters? So we want to know the net force. We know the mass is 1,500 kilograms. I'm going to put a dot next to the zero so we can treat that as if it has four sig figs. The initial velocity is 100 kilometers per hour, and we know that 1 hour is equal to 3,600 seconds, and we know that 1 kilometer is equal to 1,000 meters. So this is going to be 27.78 meters per second. And that gave me it to three sig figs, and I'm carrying one extra digit. Uh, Basically, converting kilometers per hour to meters per second is just dividing by 3.6. So we got that. We also have the final velocity is zero. So I'm looking for solution. I'm looking for an expression for the total force. And we know the total force in the x direction is equal to mass times acceleration in the x direction. But in order to have that, I need the mass, which I have, but I also need the acceleration, which I don't have. I can't use the average acceleration formula because that requires me to have the initial velocity, the final velocity, and the time, but I don't have that. I could, in principle, realize that if it's constant acceleration, then the average velocity would be the sum of 0 and 27.78 divided by 2, and then I could use the time to calculate that. That would actually work, but it's me using two equations. So you might think, oh, yeah, I remember Mr. Younger derived this equation using two equations. So that's the equation we're going to use, and we usually call this delta x. So I'm going to say delta x is 55 meters because that's what the problem told us. So first off, I'm going to say 0 squared, I'll leave off the units this time, is equal to 27.78 squared plus 2a times 55, like that. That gives me a is equal to, if I take 27.78 squared, that's 771.73. And I really should only have three sig figs there. So that means these two are that, and that's meters squared per second squared. And then that's divided by 2 times 55 meters. So divided by parentheses 2 times 55 close parenthesis, that gives me 7.016 meters per second is the acceleration. Now I can use that and say the summation of the forces in the x direction is going to be equal to 1,500 kilograms times 7.016 meters per second. And that gives me 1.052 times 10 to the fourth newtons. So that's the net force required to stop a car moving at 100 kilometers per hour in a distance of 55 meters. Anybody have any questions on that? I see people are chatting me your first and last name. If you haven't done so, please do so now. We're almost finished. I'm going to turn to another example, specifically a conceptual example, what makes a car go forward. In this case, I want to tell you exactly what's going on. So when you have a car and you're driving it, you normally would push the accelerator to make it go. Now, what that does is sends more fuel to the piston chamber. The piston chamber getting more fuel is going to basically cause an explosion. The explosion is going to push the piston down, turning the crankshaft. The crankshaft's going to turn the drive shaft ultimately, and the drive shaft's going to go through the differential to turn the axles, front or rear, depending on what kind of drive it is. That's going to attempt to turn the wheels forward, assuming you have it in forward or drive. But if the friction force isn't great enough, then your tires will spin out, which you've probably seen on dragsters and stuff like that before. But if the friction force is great enough, then it'll try to turn, but the friction force will stop it from doing so. So the friction force on the tire is actually what pushes the car forward. That's not usually understood. Now, what I want to point out to you is that objects, inanimate objects, can actually apply forces to other objects. That might not seem crystal clear to you, but if you imagine me sitting on a table, you would say, okay, Newton's first law says Mr. Younger's sitting still, and he's still sitting still, and he's still sitting still. So the net force acting on Mr. Younger must be zero. That's what we conclude from Newton's first law of motion. But when you look at Mr. Younger, you only know of one force acting on me. It would be the force of gravity pulling me down. So by necessity, you understand that there has to be at least two forces because something's got to cancel that force out. Well, it turns out there's a force called the normal force, and it's called normal because normal is the mathematically correct term for a vector being perpendicular to a surface. So uh, a table actually applies a normal force to me. If you didn't think the table was capable of doing it, imagine an elephant sitting on it, and you'd quickly say, "Oh, okay." Well, when the elephant sat on it, obviously it asked for a force that was more large than the table was capable of sustaining, so it just collapsed. Therefore, I understand now that there must have been a force before. So that's a way of looking at it. But that normal force is important. So let me show you really quickly how we could treat that. So if you have here an object of mass which is equal to 10.0 kilograms, then when we use Newton's second law, in this case I'm using it in the y direction, what we want to do is have a free body diagram. This is called a free body diagram, or FBD. And what I have here is an object that I'm going to treat like it's a point mass. It's a mass equal to 10.0 kilograms. What I know is in the negative direction of the y is the weight, which equals m times g, which is 98.0 newtons. Now, if it's sitting on a tabletop, then I know that upward force is what I call F normal. Sometimes I'll use just a plain N. Sometimes I'll use a F with an N. Your book does the same thing. But in this case, if it's me or this box sitting perfectly still, then the normal force is given by the summation forces is equal to mass times acceleration in the y direction, but it's sitting perfectly still, so the acceleration is zero. Therefore, you get Fn plus negative 98.0 newtons is equal to zero. So the normal force is equal to 98.0 newtons. Now, if instead you have the same object, but this time we've got a person pushing down on it with a force of 40.0 newtons, And then we also have the weight, which equals 98.0 newtons. Then we can see that the normal force, again, this is sitting on a tabletop, but someone's now pushed down on it with a force of 40 newtons. Now we can see that Fn plus negative 40.0 newtons plus negative 98.0 newtons is equal to zero. So we see the normal force is now 138.0 newtons. If someone instead pushed up on the box or lifted up on the box, then we would have a force, let's say 40 newtons upward, but we'd also have a normal force Fn acting upward, and we'd have weight equals 98.0 newtons acting downward. So now in this case, we'd get F normal plus 40.0 newtons minus 98.0 newtons is equal to zero again because the box is sitting perfectly still on the tabletop. So this time we get the normal force is actually equal to 58.0 newtons. And that's it. That's all we're going to be able to do. Uh, Time is up. You should look at the elevator problem, but we'll discuss that next time. You guys are free to go. I'm going to wait for the last person to leave. That includes Colin if you have any questions. If not, I can always address you by sending you a text message or something like that, Colin, if you have to split. Or I might even make up a problem helping you out. I remember which problems it was. I think it was 3.53.
Yeah, I think the problem we went over would also cover the river one. The only other thing I really had issue with was I know the range, how to get the range.
Right.
It's just the fact that it's at an elevated one that was throwing me off because I couldn't figure out how to
Gotcha.
um, add any
I'll probably
extra
work
height.
one of those anyways, just as a video. So I might be able to do that in the intervening period. I do recommend you guys subscribe to my YouTube channel so you'll get a email whenever I post something new on it. So you might want to do that. Feel free I mean, I'm not making any money off of it or anything, so you can certainly unsubscribe later. I'm not like I'm trying to, get any money off of you. But by all means do that, and that way you'll know when I do post stuff. Otherwise, you're just going to find out by my list being updated. And I do have a list. It's called My Video List by Austin, and it's listed in your in the helpful documents and links. So have a good one, everybody. Colin, are you going to be able to stick around, or do you need to split?
I don't need to split.
Okay, cool.
I'm good.
Okay, let me work a projectile motion problem with it on an incline then, because that'll probably help you most. Ian, did you have anything? Was it the PHET tutorial projectile motion? Was that the one, Colin, that gave you elevated height?
No, it was the hold on. I have it
3.35 maybe?
uh hold on. Yeah, 3.35. Just
Okay,
because I can
gotcha.
do the majority of it. It's just like getting the extra 2.1 meters higher than it is like I figured that'd be like an A squared B squared one, but I was
Gotcha.
having trouble figuring out exactly how to do that because I wasn't sure about the angle it would be coming down at that point. Because if I
Gotcha.
had the angle for that, I'd be able to figure it out. But
All right, so this is problem 3.35. It says a shot putter throws the shot of mass 7.3 kilograms. I'm going to go ahead and record that, even though it might not matter at all, with an initial speed of V0. That's a variable at an angle theta to the horizontal. Calculate the horizontal distance traveled by the shot if it leaves the athlete's hand at a height of h meters above the ground. So we're looking at V0 being 15.0 meters per second as one, and the angle theta as being 34.0 degrees.
yes.
And what? Oh, the hand height is 2.30 meters. So
If
I'm
it
going to go
was
ahead and
on,
go ahead.
yeah, I was gonna say, just say if it was like on the ground, if it was landing at an equal point, I can use the range one for that. It was just
Gotcha.
the fact that it's a different.
So this is the height h, and what we're picturing here is an angle theta with a velocity v0 equals 15.0 meters per second. But what's going to happen is it's going to do this and land down here. So this is my y-axis, this is my x-axis. And what again we're going to do is we're going to imagine the motion in the vertical dimension to figure out basically how much time it has in the air before it reaches a height of zero, which means it hits the ground, and then that'll tell us how far it's managed to go to the right during that time. In order to do that, I first have to take this 15.0 meters per second at 34.0 degrees, and I have to convert it to X and Y components. So this is V0Y and this is V0X. And V0X is going to be 15.0 meters per second times cosine 34.0 degrees. And
Yes,
that's going to be,
12.4 or
yep,
12.4.
12.436. I'll just carry a couple extra ones. 12.436. That's two extra sig figs, so that's plenty good there.
Yeah.
And V0Y is 15
Uh,
times the sine of 34.
8. Yeah, that one was
Thank you.
8.3879.
3879. Very good. Meters per second. So the equation in Y motion is negative 4.90. I'm going to leave off the units. T squared plus 8.3879 T plus H, which is 2.30 meters. So that's the Y coordinate at any point in time after it's shot, and we're assuming it was shot at T equals zero. The X, on the other hand, is equal to x0. Well, it's actually equal to the same equation. We could still write 1 half a sub x t squared
Uh,
plus
sure.
v0 xt plus x0. But that's zero and that's zero. So it just becomes, which I think this is what you're getting ready to say, 12.436.
No, I was going to say I looked at the problem again, and it's a 2.1 meters, not 2.3.
Oh, the solution I'm pulling up right now has it in terms of 2.30, so I'll work it and I'll just check my answer. It says my answer is supposed to be 24.3 meters.
Oh, okay, that's a variable one then.
Yeah,
Okay.
every
I
time you
noticed
turn
that
it
some
on, it's a different set of
over again,
numbers.
some of the numbers are variable. Okay.
Exactly. So
Yeah.
all we have to do is figure out at what time does y equal zero. So y equals zero implies zero is equal to negative 4.90 t squared plus 8.3879 t plus 2.30. Now, that might seem complicated, but luckily we have the quadratic formula. So t is going to be negative b, which would be negative 8.3879 plus or minus the square root of b squared. So 8.3879 squared. You should try this sometime with the units in there so you'll see how beautifully the units work out, but it's really kind of neat. So b squared minus 4 times a, which is negative 4.90 times b squared minus 4ac, and c is 2.30. All that divided by 2a, and a, of course, is negative 4.90, so 2 times that is going to be negative 9.80. So this is going to be 8.3879 plus or minus 8.3879 squared is going to be 70.357. plus 4 times 4.9 times 2.3. That gives me to 3 sig figs, that gives me 45.08 with one extra sig fig. A square root under that, and the 5 and the 7 were not sig figs in that other one. So I add another 0 on that for that. And then this is all divided by negative 9.80. So now I've got 70.357 plus 45.08 gives me 8 point, that was supposed to be a negative 8, by the way, negative b. So that's negative 8.3879 plus or minus the square root of 115.37. Now, they were only good to one decimal place, so that 7 is not a sig fig. So now at this point, I'm going to take the negative divided by a negative, and then minus a negative is going to make nothing but negative, or it's going to make nothing but positive. If I figure out what the square root of this 115 is, then that's 10.47. So now I'm going to get negative 8.3879 plus or minus 10.744. And that should really be 4 sig figs in this case. So I'm going to say that's not a sig fig. And then all that divided by negative 9.80. Now we can take the top sign. It would be negative 8.3879 plus 10.744. Now I'm going to divide that by 9.8 negative. That's going to give me a negative 0.24042 seconds. Or, and that one doesn't make any sense. That's basically how long ago the projectile would have had to leave the ground to hit the height of 2.30 meters at the angle that we had at the 15 meters per second that we had. So that one's not
So
very
just reaching that, so just reaching the height.
exactly. Yeah, that's what would happen. So in eight, let's see, negative 8.3879 minus 10.744. That gives me a negative 19.139. Now I'm going to divide that by negative 9.8, and that's going to give me 1.9522 seconds. That sounds a lot more reasonable. The 7 and the 9 were not sig figs, so I had two decimal places. That would be 3 sig figs. Uh,
Okay.
Yeah, in this case it'd be 4 sig figs, so that's fine. Then divided by 3 would be 3 sig figs, so that'd be that. So that's the number of sig figs. It should be 1.952. Now we can plug that in the x equation, and that's going to be 12.436 meters per second times 1.9522 seconds. And this is supposed to be 24.3, and I got 24.7, or excuse me, 24.277 meters. And that's exactly what they had because they wanted 24.3.
All right. I
Does that help?
have yes, though I have two probably kind of dumb questions.
Okay.
One, if that's the time from it reaches its height, wouldn't you need to add in the other, like the previous one is, why don't you need to add in the previous one as well to get from the starting
Oh
point?
no. Okay. So the negative time was what I meant is it's part of imagining an entire parabola that starts on the left hand side. Let's say if I added this part of the motion right here, this time right there is the time at which a projectile could have left from this blue dot on the x-axis and reached this other blue dot with a velocity of 15 meters per second at 34 degrees.
Okay. And
So
the
all I was doing
other,
was, go ahead.
sorry, and the other question was less over this and just how did you know to use the quadratic equation? Just because the quadratic equation is one of those things where I've seen it a bunch, but I've never understood when to use it. It's just one of those equations that I have trouble with.
Yeah, if you ever have an equation that has not only a variable squared, but also the variable to the first power in two different terms. So you got one term that has like t squared or x squared, and then another term has a t or an x, and then all that added up gives you zero, then that is a quadratic equation. So the form, by the
Okay.
way, is just a times x squared plus b times x plus c equals zero. That implies x is equal to the negative of b plus or minus the square root of b squared minus 4 times a times c over 2a. So notice in the equation I wrote on the left, all those are pluses. So if any of these numbers are negative, that means you got to plug in negative numbers for them because the equation expects it to be ax squared plus bx plus c.
Okay.
So if you look at the equation we had right here, if this y is zero, then clearly it's going to meet that. Or even if it's not, if it's just a number, then it can be combined with this 2.30, and then you'd have a zero on the other side. So that's when you use it, is basically when you have both the squared term and the linear term and a constant. If you don't have the constant, you can actually do it a lot easier too. For instance, if you had 3t squared plus 4t equals zero, that one you don't have to use the quadratic formula because you can just factor out a t on both sides, and it'd be t times 3t plus 4, close parentheses,
Okay.
equals 0. So you wouldn't have to use a quadratic for that.
Okay.
Does that make sense?
Yes, sir. Thank you.
No problem. I hope that helped.
Yep. Sorry, I had so many questions about this.
Oh
This
no, that's
was
fine.
just
No, that's exactly what I get paid the biggest bucks for. You know,
okay.
that's why I'm a professional athlete. But yeah, feel free. Send me a text message if you have any other problems that you need help with. Remember, if they're one of the multiple choice from practice test or whatever, make sure you let me know by sending me not only a picture of the question, but picture of the multiple choice answers. But other than that, just send it to me and I'll do what I can to help you. Also, I'm going to mention it here because I seem to have forgotten to mention it in class. I did make online test two available and the practice test two available. Uh, the online test is due this Sunday, but I should have mentioned that to everybody. But it's on their syllabus and it should have popped up on Canvas as well. But I just want to make sure I let you know as well as everybody that watches this video.
Okay.
All right. Have a good one, Colin.
Thank you.
You're welcome. Ian, are you still here? Do you need anything? I guess Ian's not here. So I'm going to say stop share. And I'm going to say thank you for coming, everybody. Bye bye. Bye bye. End.